Good morning and welcome to this next lecture on vibrations of plates and shells. So last class we left off at this point where we just mentioned that when you have circular vibrating objects that are closed in the theta direction, then you get two sets of modes, otherwise the information is incomplete. Okay, you will get a cos n theta type of modes and you will get sine n theta type of modes. Okay. So now let me write down the equations for the ring. Okay, these are the equations for the ring, for a circular ring, okay, which is a shortened version of a cylinder, shortened in the x direction. Okay, the equations of motion, both of them are d over a fourth minus del 3 u3 del theta cube plus del 2 u2 del theta square plus EH. So I will call this K here, sorry. So K, the membrane stiffness, K by R square del 2 u2 by del theta square plus del u3 by del theta is equal to rho h u2 double dot. Okay. Similarly, the other equation is d by a4, a to the power 4 del 3 u2 by del theta cube minus del 4 u3 by del theta 4 minus k by r square del u2 by del theta plus u3 is equal to rho h u3 double dot. Okay. Now what we do in here is that we substitute for u3, okay, and u2 is equal to some u 2n e to the power of j omega nt, and u3 is some u3n e to the power of j omega nt. Okay, if you substitute that, then what happens is all of these will become u3n and u2n, and this becomes minus rho h u2n omega n square, and this becomes minus rho h u3n omega n square. Okay, so u2 is the u theta movement, please remember, theta direction movement. Okay. Now further, u3n, okay, can be written as an cos n theta minus phi. Okay, and u2n, so I will write theta because textbook does so, u2n is u theta n is equal to bn sine n theta minus phi. Okay. Now you can ask, how did you get this? Okay. One is you can use the traditional Laplace transform method to get this, okay, the Laplace transform, or by playing with it a little bit and using some intuition, physical intuition, which the textbook briefly discusses. Okay. You can find that as u3 goes through the maximum motion, u2 goes through the minimum motion, minimum, okay, displacement. Okay, you can figure that out. So u3 is cos n theta type term, and u theta is at that moment sine n theta term. Okay, when u3n is cos n theta term, u theta n is sine n theta n term. Okay, so I said this is one set of modes. If you just stick with it, some displacement is missed out. Okay, so u3n can also be sine n theta type of modes. At the same instant, u theta n will be cos n theta type modes. Okay, so in order to represent these two together, okay, the combination looks like this. Both cosine and sine are available in both places, but they could be phased. Okay, sine here could be phased relative to sine here, or cos here could be phased relative to cos here. Okay, that means when cos occurs over here, cos need not occur here, sine can occur here. That is the phasing. Okay, and therefore to accommodate that combination, we have cos n theta minus phi, sine n theta minus phi. Okay. Of course, at any instant cosine here has to be matched with sine here, that the equations will tell you. Okay. Cosine here will not match with cosine here because of the derivatives. You can see that you get third order derivative in theta, so that becomes 2 becomes cos, third becomes sine. Okay. Then u2 has 2 orders, so sine twice will become sine. Similarly, u2 has 2 derivatives with theta, it is back to sine, and u3 is one derivative from cos, and thence it is sine. Okay. And therefore, all of them are sine. Okay. Similarly, here u2 has 3 derivatives, so 2 is back to sine, 3 is back to cosine. u3 has 4 derivatives, so 4 derivatives get it back to cosine. Similarly, one derivative with theta gives you cosine, and u3 is already cosine. Okay. So the cosine here has to be matched with sine here. Okay. But there are also the other modes. Once cosine has been completed, there are the sine modes here. Okay. And once sine has been completed, there are cosine modes, otherwise the information is incomplete. So this phasing kind of represents the actual orientation of the mode, and also the fact that you have both sine and cosine. Okay. So having said that, if we substitute this back into these equations now, what do we get? We get a matrix again, we get a matrix. Okay. And we get a n and bn. It will not be very difficult to actually do it, so let us do it. So this term, let us say, let us number this 1, 2, okay, and 3 and 4. Okay. So 1 gives me what? D over a fourth del 3 u3 del theta cube, 3 derivatives of this. So I get 2 gives me minus, third gives me a n minus n cube, okay, sine n theta minus phi, plus 2 derivatives of u2 gives me bn into minus n square sine n theta minus phi. Okay, from now onward sine n theta minus phi is capital S, cosine is capital C. Okay, then the second term k by r square, two derivatives of u2 or u theta is bn minus n square capital S plus one derivative of this, which is a n into minus n into sine. Okay. Okay. So if I have to fill this matrix, so I have rho h omega n square from here, let me fill it up, then we'll see. Okay, so third one, let's do third one. Third term d by a fourth d by a fourth, confuse the notation here, d by a fourth, three derivatives u2, 2 gives me minus n, so I get bn minus n cube and cosine, then a minus four derivatives with theta gives me a n into n fourth back to cosine. Okay, then the fourth term gives me minus k by a squared one derivative at theta gives me bn, n and c, and no derivative gives me an c. So if I try to fill this up, here, okay, so first equation I get plus rho h bn omega n square bn. Here I get plus rho h omega n square an. Okay, so let's do this here. So I get, if I keep these out of my sight, minus n cube minus dn cube minus dn cube by a fourth. Okay, then here minus nk by a square, minus nk by a square. Okay, then I get a plus rho, let me expand it, so I get a rho h omega n square from here Bn, then I get a minus n square d by a4 minus n square d by a4, so it's done. Then minus n square k by a square, minus n square k by a square. Okay, that is the second equation. Then the first equation, this one, the bending equation, I get for A minus n4 d by a4. Okay, first of all I get rho h omega n square, then I get minus n4 d by a4, d by a4. Okay, so I am done with this term. Then minus k by a square, k by a square. Okay, then for the B I get minus n cube d by a4, minus n cube d by a4. Then from here minus n k by a square, minus n k by a square. So there is a separation here. Okay, so this is what I get now. Okay, now what do we do from here onwards? As usual, for a non-trivial solution of an and bn, the determinant of this has to go to 0. Okay, so how does the determinant look like? Determinant looks quite complicated. So, and we have a omega n square here and omega n square here, so we get a fourth order. So let us see how it looks like. So this thing in a collected, terms collected form looks like omega n to the power 4 minus k1 omega n square plus a k2 is equal to 0. So fourth order, and so you get 1 omega n1 square, and then you get second omega n2 square. So you get two sets of natural frequencies. Okay, you get two sets of natural frequencies. So what is k1 here? K1 here is n square plus a1 by a square rho h n square d by a square plus a k. Okay, and k2 is equal to n square minus 1 whole square by a to the power of 6th rho h square into dk. Okay, one thing to be noted, we will use it later, is k2 is equal to 0 when n is 0 or n is equal to 1. Okay, so we will use it later, keep a note here. Okay, so now what is omega n1 square set of natural frequencies? Those are k1 by 2 into 1 plus or minus or omega n1 square, yeah, in one shot omega n square plus minus square root of 1 minus 4 k2 by k1 square, which means the first set omega n1 square is equal to k1 by 2 into 1 minus square root of 1 minus 4 k2 by k1 square, and the second set is k1 by 2 1 plus square root of 1 minus 4 k2 by k1 square. Okay. Now let us look at this. Let us look at this term over here. So before I proceed, okay, I should comment here that this matrix and this vector equated to 0, that is problem solved. Okay, so let me do that first here. So you set the determinant to 0. So you set the determinant to 0. You get your omega n1 square, you get your omega n2 square in any manner, closed form or numerical. Okay. And then if you substitute it back into the equation, let us say you substitute back omega n1 square set of equations. Okay. Then what will happen is because these are eigenvalues, the matrix is singular, that means it drops its rank. So you can solve for an in terms of bn or bn in terms of an. Any equation is equivalent, any one equation is equivalent. So you will get something times an plus something times bn equal to 0 from the top equation, let us say. Then you can solve an in terms of bn or bn in terms of an for every omega n1 square value. Okay, that means omega square 0 1, omega square 1 1, omega square 1 2 1, omega square 3 1, and so forth. Okay, first set. Similarly, omega square 0 2, omega square 1 2, the second set of natural frequencies. Okay. Now it will turn out that for one set of natural frequencies, an by bn is much greater than 1, and in the other set of natural frequencies, bn by an is much greater than 1. Okay. If you remember, an was for the transverse U3 movement, and bn for the tangential or torsional movement, torsion. And therefore, one set of natural frequencies will say that they are dominantly transverse, and the other set of natural frequencies say the displacement is dominantly torsional. Okay. So it is interesting that it is no frequency is saying only transverse, okay, only transverse, and no equation is saying only torsional. That means in one case an should be 0, in the other case bn should be 0. No, both are non-zero. Okay. But in one case an is much bigger, in the other case bn is much bigger. That means the ring, every point at every natural frequency has both radial or flexural movement, okay, flexural movement, and tangential movement. So every point, if I take this point out, that point has radial movement and it has tangential movement. But at some frequencies it has dominantly radial movement and a small tangential movement, okay, and in some frequencies it has dominantly tangential and small amount of radial movement, okay. That is seen even in the equations of motion because they are coupled. A single equation has u3, u2, u2, u3. This single equation has u2, u3, u2, u3. So they are coupled. the motion in the transverse direction and the motion in the theta direction, they are coupled together. So, you can't separate them. Okay. So, you cannot have only radial or only torsional. Okay. So, that is what this system is saying. However, one set is going to be dominantly transverse, one set is going to be dominantly torsional. Okay. And these torsional frequencies will be very high in value, their numbers, because the ring is very stiff in torsion, okay, whereas it is quite limp, less stiff in the radial. So, those natural frequency will be smaller. Okay. So, that is the way to solve it, and it is solved by this stage, it is solved and the problem is done. So, you have both the mode shapes and the natural frequencies, and mode shape, mind you, is both of these together. Okay. So, at a certain omega n frequency, you have u3n is a n cos n theta minus phi, and then the other one u2n is b n sine n theta minus phi. Okay. So, what do? You substituted that particular omega n set, let us say first set, then this matrix became singular and you found the an to bn relationship. Okay. So, if I say an by bn is something x value. Okay. So, I take bn to be 1 and I take an to be x. So, this becomes 1 and an becomes x. So, this together is a mode at omega n1, let us say. Both displacement together is one mode, okay, at the omega n1 natural frequency. So, at any natural frequency you find the relation between an and bn, substitute that over here, those are the relative amplitudes, and that together is called one mode of vibration. Okay. And in every mode there will be some transverse movement, some torsional movement. Okay. So, the problem is solved already. However, we want to get some insight, we want to get some insight into this picture. That is what we are proceeding with over here. Okay. I should have mentioned that part. So, by this stage the problem has been solved. You can either closed form or numerically find the determinant, find the values of omega n. I think you can find it in closed form because it is fourth order. Then from once you find both the sets, you can find an and bn for particular material, particular E, particular thickness, rho and so forth, and you are done. Okay. However, instead of just letting it go there, we are going to look a little bit inside and see what it means. Okay. So, that is this part over here. So, the natural frequency expression is a fourth order, okay, and then this is my k1, this is k2. So, one set is with minus here, one set it is plus over here. Okay. That is where we are at. Now, what is this term? 4k2 by k1 square. 4k2 by k1 square, that is equal to, if we substitute k2 and k1 from above, we get 4n square minus 1 whole squared d into k by a to the power 6th rho square h square a fourth rho h whole squared by n square plus 1 whole squared into n square d by a square plus k whole squared. So, if I cancel some things, okay, I cancel this with a 2 over here, and I cancel rho h and rho h. Okay, so I get 4n square by a square, n square minus 1 whole squared by n square plus 1 whole squared d into k by n square d by a square plus k whole square. Okay, and as n goes bigger and bigger, okay, I have here the n squares cancel off. I have an n square over here and an n fourth over here, so it is kind of proportional to 1 over n square, which goes to 0. Okay. Now what we are going to do to get a physical picture of this set of equations, we take a case where n square d by a square is much less than k. Okay, we will look at this case. The time has run out, so let me stop here. We will continue from here next class. Thank you.